out papers, and I'm happy to show you what I know about it. But it is more complex than simple issues in other kinds of theory. They're not simple, but other kinds of theory.
Okay, thank you. Let's meet at 10:55.
Again, a beautiful idea that would work if the universe were empty, because by the time we get there, everything has been diluted away by expansion. However, Howard Turok, you might remember, have this other tool, the cyclic universe. And so if you combine Abbott with the cyclic universe, you get here, and the universe cycles, and suddenly it's full of energy again. It's a very clever idea. It gets around the basic problem with these dynamical mechanisms like this hallucinate the universe, because you get to fill the universe for free. I'll just give you my scorecard. I meant to reverse those colors, actually. Okay. Anyway, so I want to sort of the three things to think about in evaluating this model. First, is the underlying, scale of potential plausible? So the Abbott potential requires both very tiny steps, because you need that the spacing between the steps is no larger than the current cosmological constant. Now that's not so hard to realize in string theory. You just put some fluxes on a very deep throat, and the redshifting will give you this small scale. But the other problem is that you need an enormous number of steps, because you need this stepping mechanism to cancel a standard model size cosmological constant, and so you need to order 10 to the 60th step. And this is much, much harder to realize, because if these steps, for example, are coming from brains or fluxes, by the time you get to 10 or 100, they're back reacting on the space and changing its shape radically. And by the time you get to 10 to the 60th, they'll have grown the compact space up to something that, which is much too large. Similar, by the way, large fluxes come up in these DBI, not so large, these DBI ideas. Maybe as a side effect, maybe someone will figure out some way to put a large number of fluxes into a Flavian manifold without grossly distorting its geometry and making a model of the type that works. In the topic landscape, the vacuum structure you need agrees with our best current understanding of string theory. The second test is the cosmological dynamics plausible. The S-quadratic bounce is problematic. There are certainly those who hate it. I would argue that we should treat it as an open question, being generous, but the topic landscape requires only inflation plus tunneling to very ordinary physical processes. And finally, the third test is, does it solve the third cosmological constant problem? And in this model, it's a total coincidence. There's no relation between the current matter density and the parameters determining the cosmological constant in the topic landscape. Well, it misses by 100 magnitude out of 120. So this is my scorecard, but we'll see. Yes. So how can you? They said they could have used the landscape potential. I still think. No, because their calculation depends on the fact that the steps are small. If in the landscape where you're making large steps, there's no. I believe there's no special factor that favors the smallest positive lambda. That's something to think about. But I certainly, your calculation depends on that steps are small and regular. Yes, sir. Yes. I sort of understand why it doesn't cover that wouldn't I agree with you, and I actually thought I forgot to something similar, and it might be still true, but it's not so obvious because as published in their paper, these peaks are actually I tried to draw it. It's actually a much more modulated potential. The barriers are very, very high even compared to the energy density during the hot part of the cycle. And it's not clear that will dominate. It might. I think it's a good question that needs to be checked. Okay. Yes. In a precise way. Okay. So there's two more points here on which the topic landscape speaks this idea. Number one. Just our best understanding of the dynamics of typical vacua, which have all of the fluxes in the brain. I'm talking about the KCL deconstruction and then the various things that have been inspired by it. In terms of the technical theory, that's right. No, I'm not. I'm not even sure that's good, but I wanted those colors to be flipped. I put this on deliberately this morning. Anyway. Let's move on. So here's the second idea, which has an interesting history. So this is, we say, this is Tanizaki, where you have two fields. This is like the average of a very slowly rolling field with an infraton field. And again, with no special prejudice, I've labeled these two vacuum red and blue so that I can add these. If you're sitting in the red vacuum, you're up here. If you're sitting in the blue vacuum, you're down here. And so if you think about the idea is that this potential is supposed to be so shallow that it takes a really long time to move along it. Again, this is something which is hard to realize in string theory, but that's just been our disbelief. So effectively, it behaves like a cosmological constant at any given time. And so when you get to this point, when you're around here, you think you're in a vacuum that has zero cosmological constant. And so that's good. But again, the empty universe problem, by the time you get here, all of your matter hasn't faded away. So what you need then is this, again, you need the intercom potential, you roll up here, and just when you get here, when you're right above the vacuum you want to be in, you tunnel through and drop down, and there you are, zero cosmological constant, lots of energy, our universe. So this was originally proposed by Tom many years ago, which is one of the first, the first concrete anthropic arguments for the concrete anthropic model. And also, by the way, he pointed out that you wouldn't get exactly zero. There would be a non-zero dark energy. There's no reason that you'd have to hit exactly zero. Now, Tom's idea, it didn't work for reasons that I'll come back to. But recently, Sonny Izaki has elaborated this in an interesting way. He couples these two fields together in such a way that just when you get to this point, you see this dashed line here, just when you get to this point, the potential becomes flat and you roll down from here to here. Now, to do that, you need classical fine-tuning of the potential to 1 part in 10 to the 60th. From that point of view, it's extremely contrived and poorly motivated, but it does do something which, as rarely as ever been done before, is technically natural. That is, standard model vacuum corrections just move the entire picture up and down, which is equivalent to moving it right and left, and don't change the tuning of it. So it may be the first time that someone has actually found a way to sort of technically naturally cancel the standard model effect. Besides the fact that the classic, even the classic potential is very contrived, it's actually not clear that it works, because in order to get this energy into the matter field, you need to introduce some couplings that might spoil the stability. So it may not work in detail, but even if it's wrong, my theme is that there's a large number of ideas that are wrong for a small number of reasons. If this one is wrong, it's wrong for a new reason. By the way, coming back to Tom's argument, the argument that it didn't work was that if we stay up here a little longer, the universe will expand a lot more. There'll be more of it, and so by the time it drops down, there'll be many, many more galaxies formed in those regions that stay up here and then drop down than in those that drop down at the right time. And so we'll see not a positive cosmological constant, but a substantial negative cosmological constant. And interestingly, these volume factors are now being re-examined, and there are some interpretations of them, including, I think, the one that Raphael said again, according to which I believe Tom's idea would work. Third recent idea, also I saw her in Europe, starting to put out a paper which has more or less the same observation they mentioned to me before the Lincoln paper appeared. That is, the Weber calculation requires that the vacuum will be assumed that the probability density for the vacuum is roughly flat. The argument that it's flat is that we have already reasons that lambda equals 0 is not a special value, and so it has to be flat. But in fact, there could be Cohen factors such that it's flat on average but has large fluctuations. And if that's the case, then rather than being in the anthropic range, you'll be some vacuum outside the anthropic range, which has much, much more volume because of these sporadic tunneling factors. And the one that so work, you would need many, many more vacuums to average out these fluctuations. Again, this is a larger probability, and the scale here is hundreds, and so we'd be in that vacuum rather than in that vacuum. Again, this depends on the interpretation of these large volumes, and there's always large numbers of vacuum, volumes, tunneling factors, and there's this question that someday we'll really answer to, do these large numbers really enter into the calculation of the observables? Finally, a few general lessons from model building. First, compactifications with simple topologies don't seem like they give you enough vacua. If you have only 6 handles, enough parameters or fluxes to get a dense spectrum. You need something of order of 100 handles, which is, I'll be referring to this in my favorite manifold of a course. I don't know, I think about a quantum manifold with 100 handles, but it may be that we will eventually have to think about compactifications which, instead of being simple and explicit, are enormously topologically complex. And are there any general properties that these manifolds have? You might have to even think about a typical quantum manifold with that many handles. The other general lesson is stability. This comes back again to the KKLT construction. So if you had a generic metastable vacuum, all of the vacua are metastable, all of the non-supersonic vacua are metastable. If you had a generic metastable vacuum in the middle of moduli space, it would decay with a rate of order 1 in some short distance unit, and our vacuum